L09 the spherical shell. Now for the shell, we're going to have here a thin shell. Let's go ahead and put in our axes here. So X, Z, and Y. And see, the secret here is that if we go around here, we're going to have a little thickness. A little thickness here is hollow inside. It's hollow inside. So as we spin around here, this little element of moment of inertia for this thin little band is going to be, here's R, that's R squared dm. But now our dm is made from a ribbon. I'm going to say ribbon here, because this is really a ribbon effect. Now there's a better diagram here for you in the text where we have this little ribbon that's going around and it's hollow, empty inside. So here, this is capital R, and we use this angle as theta coming from the z-axis, which is conventional in upper level physics courses. So this is R, and then here, this is big R, and we have a delta theta inside there, and then this little arc length here is R d theta, and we are at a distance z to get to that little ribbon, and then dz is the infinitesimal along the vertical. So here we want for the mass, it's a surface density times dA, and the surface density here is the mass of the shell times the area, which is 4 pi r squared. Now you can get that result quite quickly. Watch this trick. If you forgot that, look at the volume, 4/3 pi r cubed, and go dv, differential. This is 4/3 pi, taking derivative, 3r squared dr. These threes cancel, and you get here 4 pi r squared dr. So the differential volume of a sphere is the area of the shell times a little dr. Isn't that cool? So this has to be your surface area, and this is the thickness of the shell. That's very quickly derived from the volume taking a differential. So we're ready to do the problem now. Let's summarize what we have. We have dm is sigma dA, and the sigma is the total mass over the total surface area, like that. I like to use for densities, linear density lambda, surface density, area density, sigma, and then rho for the volume. So this is an area case. So now we're ready to put it all together. di is equal to, we have the r squared, and then we have the dm, which is going to be the sigma, and we have the dA. Now, what is the differential area? Well, the differential area, so we come around here, that's a little r. This is your r d theta, this way, the arc length. And we're going to go around, all the way around, 2 pi r gets us around in that little thickness to get us the area. So we want 2 pi r. Now, you got to be careful that that r is the little r. The little r is the one that takes you all the way around. The big R times d theta gets you that little thickness. So 2 pi little r, and then we have d theta. Going back to this diagram, 2 pi little r gets you all the way around, and then you take a little r d theta, and that's going to give you the area of that little ribbon that goes all the way around. So we have it, and we go ahead and put it down here. We have 2 pi r cubed and a sigma in there. So 2 pi times the sigma times the r cubed, and then here we need to have r d theta. We forgot the r there, so put the r d theta. And that gets us everything that we need to do the integral. So let's just remind ourselves that this little strip here has an angle theta. This is big R, and there is the little r. This is your z-axis. And your little thickness there on the slant is r d theta. So we have to get everything in terms of the variable of integration. I'm going to go for theta, since I already have a d theta there. And this little r, if I go ahead and bring this out like this, little r, and there's the big R, and this is the angle theta. The little r is the big R, the hypotenuse, times the sine of theta. So that gets me the little r, which I'm going to substitute in. And then for the di, I'm going to have 2 pi sigma, and now I'm going to have this cube will give me an r cubed with another r will give me an r to the 4th, and then I'll have, when I cube this sine, I'll have the sine cubed of theta, d theta. So this is it, and now I'll go ahead and put in what this sigma is. It's m over 4 pi big R squared. So we get some cancellations in here. We're going to get the 2 canceling partially with that 4, which will give us a 1/2. Then the pi's go away, and we'll have the m, and 2 factors of the big R go away. So we'll have this 1/2 mr squared multiplying the sine cubed with the d theta. So the integral that we're interested in doing, I'm going to integrate the theta from 0 all the way down to pi, but since the hemispheres contribute equally, I'm going to put a factor of 2 in front. Now what are all these constants here? 1/2 m r squared, and then the integral from 0 to pi over 2 come down to 90 degrees. That's a hemisphere, and the 2 takes care of the lower hemisphere, and this is sine cubed theta d theta. These cancel the 2's, so we have mr squared, and then we have the integral from 0 to pi over 2 of sine cubed theta d theta. So that's the integral that we're interested in doing. Now that sine cube looks a little tricky, so what we're really interested in doing, let's go ahead and extract this integral. The integral, just I sub s, just to call it something different. I sub s for the sign. This is going to be 0 to pi over 2 times the sine cubed theta d theta. So what I'm going to do with this is I'm going to replace this with a sine squared of theta and a sine theta. And then this is going to be 1 minus cosine squared theta. And the reason why I'm doing that is because the derivative of the cosine is related to the sine. I'm going to be able to integrate this. In other words, my strategy is going to let u equal the cosine of theta, then du is going to be minus the sine of theta d theta. So I'm going to have like a du here and a 1 minus u squared. That's going to be like easy to do, that integral. So that's the logic here. Now we have to be careful when you switch the variables. As the theta goes from 0 to pi over 2, what's happening to the u, this new variable, because we're going to be substituting? Well, the new variable, if you put in 0 for the angle, you would get cosine of 0 is 1. Then if you put in here pi over 2 for the cosine, you'll get 0. So the u goes from 1 to 0. So let's see what we have for the integral. We're going to go from, with the u variable, we're going to go from, I'm going to explicitly say this is u, going from 1 to 0. And then I'm going to have here 1 minus u squared. And then the sine of theta d theta is equal to a minus du. So if you want, you can have this d theta here hanging around. And then when you look at the combination of these two here, that's going to be minus du. And then when you look at this part, 1 minus cosine squared, that's 1 minus u squared. And then the variable limits change from 0 to pi over 2 to 1 to 0. Now we can switch the order of integration here and get a minus sign, which will cancel that minus sign. So if we go from 0 to 1, then we have 1 minus u squared du. Now you can see that this is now easy to do. So here, the first one's going to simply be u, and the second one is going to be u cubed over 3. And we're going to go from 0 to 1. So that's going to simply give us 1 minus a third, which is 2/3. So we have just found that all of this comes out to be 2/3. We have our answer. The moment of inertia for a shell is 2/3 mr squared. And the units come out right. Mass times a length squared. So that's the shell. Now I'd like to show you another way of doing this. It's always good to do things more than one way. And the trick I want to use here is related to this trick where we take a differential from a volume element and get the surface effect. Here, we know that the moment of inertia for a sphere is equal to 2/5 mr squared. But now we have to flush out the R dependence because, see, there's R dependence here. The density, see, our densities are going to be the same for the shell and the sphere, but the mass is going to be different. So we want to be careful here that we flush out all the mass, flush out all the R dependency. So that mass here is equal to some volume density times 4/3 pi r cubed. So when we do this, we get for the sphere, see, I'm about to take a differential with respect on this side, and a dr is going to show up on the right, but I want to make sure that the r's are everywhere where I can see them. So this would be 2 times 4 is 8, and 3 times 5 is 15, so 8/15. And then we have here the rho and the pi and the r to the 5th power, like this. So now when we take di of the sphere, see, we're going to then get something analogous to where we had that shell surface area times a dr. So we're going to wind up getting the shell effect here. Watch this. So we have 8/15. We have rho times pi, and then we have a 5r to the 4th times dr, taking the differential. Let me simplify this. This will have an 8/3 rho pi r to the 4th dr. Okay? So now what we're going to say is that this is equal to the I of the shell effect times dr. Just like we did over here, where we had a shell effect, surface area of the shell, times a dr. So here we have this equation. Write down I shell is equal to 8/3 rho pi r to the 4th. But now we have to be careful that the rho that was originally the mass of the sphere divided by the volume of the sphere, okay, that's what we had initially, that has to be replaced with mass of the shell divided by the surface area of the shell, because now we have an area density. This is the area density, sigma, all right, when we do the last step. So by doing that step, we have I shell is equal to, the 4 will go into the 8, and that'll get you 2/3. So this is going in for this. The pi will cancel, and one of the r's will drop out, and you'll have the mass of the shell. And that is the answer we got earlier over here. Now this is a sophisticated analysis here. So this is the straightforward way, which is my preferred way. Right to the point, we got it. But I thought it would be interesting to show how this trick, when you have volume information and you want to go to a shell effect information, how it would still work, if you're careful, with the sphere moment of inertia. taking the differential of the moment of inertia for the sphere after you flushed out all of the r dependence, since the rho is a constant, and we're taking the dr, so we get all the r's out of there. And then when we did this, we said this has to be the information for the shell. But now be careful with the shell. We no longer have the density of this for the sphere, we have the density for the shell. And we want to replace the mass of the sphere with the mass of the shell in our final answer. And the r is going to be the same. So we have the r there, but it's 4 pi r squared for your area density. And then when you plug that in, it pops right out, the 2/3 mr squared. So think about this, you rest a little bit, go back, because it's a little tricky, and understand another way to solve the problem. Now, what is a good example of this? Well, basketball's got air inside, so compared to the air, you could basically say it's like a shell. And let's figure out the kinetic energy of a rolling basketball like we did before for the rolling sphere. So the kinetic energy would be 1/2 mv squared plus 1/2 I omega squared. And the I is going to be 2/3 mr squared. And then here we're going to have, remember that V is omega r for something that's rolling, capital R in this case. So this is going to be V over capital R, and it gets squared. The r's squares will cancel, and there's a 1/2 that's here in the front of this. So when you work on this, you'll have, I'm going to leave the 1/2 there since I have a 1/2 up there. 1/2 times 2/3, this is going to be mv squared, since the r squareds cancel. And really I'm adding here, I have a 1/2 and I have an m, but I have a v squared, one of those up here, and then I'm going to add a 2/3 times 1/2 mv squared. So really I'm adding 2/3 like this, which is going to be 5/3. And the answer for the kinetic energy is going to be then 1/2 of this, 5/6 mv squared, where v is your translational velocity of the rolling shell. Now what about an edge? So in other words, the one that we did there with the shell is through the center, so the center of mass. But if you want it, let's say, hanging from the ceiling like this, and let it go back and forth this way about this pivot point, then you have the I, for this case, is the I center of mass plus, and you're displacing this, the distance r, plus m. This is your parallel axis theorem. So the d is going to be r, and the I is your 2/3 m r squared. So you're basically here adding mr squared to the 2/3 mr squared, and 1 is 3/3, so you're going to have 5/3. So this is about, say, I'll say about the top of the, like you're hanging it. So this is going to be 5/3 mr squared. And in this picture here in Croatia, excellent picture there, dedicated to the public domain, of a ball, and we're approximating this as a hollow ball that's hanging here, a disco ball, since the decoration's on the outside. That's the main thing, with the lights hitting it. And here you have found with this analysis that the moment of inertia about this top pivot point is 5/3 mr squared. Fine ball found in the Garden Brewery, Zagreb, Croatia. I believe that's the only brewery that displays a disco ball.